Hello, this is Team 3, and we are going to present the final result of our course project of CS572. For the brief introduction of the paper, we choose to improve the paper with the title of Cascade Flight Control of Cold Water based on deep reinforcement learning. In this paper, they try to solve the problem that comes with the classical deep reinforcement learning for robotic control, especially the drone control, which consists of long training time, complicated hyperparameter tuning, and black box dynamics. And to solve these issues, they propose the cascade deep reinforcement learning, where the dynamics of drone are divided into 6 subsystems, and these 6 subsystems are individually trained and connect to each other instead of training the whole single system. And to do that, 3 methods are involved. First, since the dynamics of drone are coupled, it is linearized to decouple, and so the connection between each system can be obtained. Second, the cascade control structure are construct, where the resource of the train network of the position system will become the input for the train network of the attitude system. In this way, each subsystem can be trained individually and connect to each other after that. And in fact, the networks are trained sequentially, where the network of the attitude system will train first, and then the network of position system after that.
Lots of computation and hyperparameter tuning in DRA leads to long training time. The graph shows the time needed to train a UAV with DRA method. In paper 1, DRA is applied to track a desired angular velocity. In 2, the multiplicative reward is used to RL for controller tracking desired angular velocity to prevent underestimating reward terms. In 3, the agent runs low-level dynamics of the UAV and uses the run dynamics to hover. The selected paper tried to improve the training time and achieve tracking performance with short training time. Now we will explain what we did for replication of the original paper. For test of the performance of the controller, we added visualization of the flight of the drone. After that, we trained the model using the exactly same method with the paper. Lastly, we applied PPO from stable baseline 3 to see how well the model is trained with another algorithm than TD3. First, we trained the model using same method with the original paper. We trained the controller for roll pitch U, X, Y, and Z with TD3. Left image shows the desired and drone position in a test. Right video is the visualization of the flight during the test. After that, we train the roll pitch U, X, Y, and Z controller using PPO from stable baseline 3 library. Furthermore, we use same observation, action, and reward, and only change the training algorithm. As previous page, left image shows the desired and drone position in the test, and right video is the visualization of the flight during the test.
For our proposed improvement, we want to remove the small angle assumption as in the paper and utilizing the full dynamics of drone. And to do that, there are 3 main modifications to original method. First, the output of the position network will be treated as acceleration rather than the thrust and the desired low and pitch angles. And second, these desired accelerations has to transform to the desired thrust and the desired angular velocity using the geometric control method. And third, the attitude system has to change from receiving the low pitch and yaw angles as an input to receiving the desired body angular velocity instead. And for the improvement step, we first modify the attitude system As already presented in the progress presentation, the input of our network structure will be the desired body angular velocity, and the output is the corresponding torque. And we also modify the reward function by multiplying the current error with the positive constant and include the error integral term of the error to prevent the steady state errors. And then we train this attitude network. And after that, we include the transformation block between position system and attitude system. This transformation block will convert the desired acceleration to desired body angular velocity and thrust. The way to convert from the acceleration to thrust and body angular velocity as in the slide and can be found in the reference 1 and 2. And for the final improvement step, we modify and train the position system. But however, there is a certain issues in which the desired acceleration in all axes are needed altogether to compute the desired angular velocity, which will be fed to attitude system. But with the cascade structure and hierarchical training approach as in the paper, all of them cannot be obtained all at once if we individually train the subsystem. And so we tackle this problem with two approaches. For the first approach, we propose to use one single position network. And so the input to this network will be the difference between the desired and the current position, the difference between the desired and current velocity, and the current accelerations, which are 9 dimensions. And the output of this network will be the desired acceleration in 3 axes, which are 3 dimensions. And for the reward functions, we will use the same function as in the attitude system, but we also include the velocity error to the reward term. And since the dimension of the network increased, we also increase the hidden layer from 32, which is used in the paper, to 64. And we train the network with 3D3 algorithm. And the result as shown in the videos, where the drone tracks the reference trajectory as a tilted circular path in 3D space. And as can be seen in the video, the drone can move and travel along the specified trajectory. And for the tracking performance, the left picture shows the tracking result in x-axis, with the blue curve is the reference trajectory and the orange curve is the drone trajectory. And in the right picture, it shows the trajectory of the drone and the reference trajectory shows in the 3D space. And it can be seen that with our proposed method, we can achieve the better tracking performance, in which the root mean square error in our case is less than the smaller than the root mean square of the papers.
For improvement, our second approach is using one controller for each axis. Therefore, we use 3 networks to control position as in the paper. The input of each network is difference between desired and current position, difference between desired and current velocity, and current acceleration in each axis. Output is the desired acceleration in the axis. The reward is the norm of current error in the axis minus k times norm of previous error. The model is trained using PPO algorithm. Here is the result, and you can see the drone flies along the desired trajectory. And you can see the trajectory tracking result and we compare the result with the original paper. And you can see the first row is the result of our approach, and the RMSE was 0.2778, and the RMSE of the method of the original paper was 0.4395. And you can see our second approach is also have less RMSE. The main contribution to the improvement in tracking performance is the inclusion of the error of velocity tracking in the real function. In original paper, only the error in position tracking is considered in real function, and this is considered as stabilization of a certain location, not tracking trajectory. But now we consider the tracking trajectory problem. When fluid dynamics is utilized, drone is no longer operating in near hover condition, as in small angle assumption case, resulting in more agile and thus more accuracy in tracking performance. The original paper handled the problem of the training of a drone by using the hierarchical structure of the controller. We replicate the original work using the same method and another algorithm. We try to remove the small angle assumption by using a transformation block and attitude controller. We tried different two approaches for position controller, and both approaches were better than original paper. Thank you for listening.